So today we're going to start taking a look at neutral geometry, and to start with, we've had several different kinds of geometry. You've talked about incidence geometry specifically, where we don't have a parallel postulate, right? And then we've also talked about the fact that if we introduce a certain type of parallel postulate, then we create different kinds of geometry. In particular, we talked about three different types. Euclidean, where we spent most of our time. We briefly talked about the elliptic parallel postulate and then the hyperbolic parallel postulate, and we will talk more about in particular, the hyperbolic parallel postulate later. But before we get into any of those, we kind of got to figure out why it is or what it would do to create these other parallel postulates. And in order to do that, I'm going to define what neutral geometry is. So a definition, neutral or absolute geometry is based on the incidence betweenness and congruence axioms. Along with the continuity axiom most of the time. It is neutral. This is where the word neutral is coming from. On the issue of the parallel postulate. So far, so good? Nice. Okay, a note about this valuable information. There is actually a name for models in this type of geometry. So any model for neutral geometry is called a Hilbert plane. And a couple of examples. One we've actually talked about both of these, but one you know very well is the Cartesian plane. Our Cartesian plane is such an example. The other one I have mentioned before, and I'll draw you a picture to remind you, is called the Klein model. I don't remember if I identified it by name before, or if I just spoke about it. In the Klein model, points are points inside a fixed circle. We had one similar to this on your exam. And lines, instead of it being diameters, like what we did on our test, lines are actually chords of the circle. so we end up with things that look like here are 2 points, and then unlike our test where we had to have a diameter that connected them, here it's only a line that connects, or a chord, excuse me, that connects them. Like so. So if I'd drawn that well, it would be a little more convincing, but it's not too bad. We can actually connect any 2 points, and that was where we failed on our exam, to actually have a model. Do you remember that? You can't connect them all with diameters, but you can connect them with chords. So this is what we have for a Klein model. Now each of those have different versions of the parallel postulate. It's important to realize, of course, your Cartesian plane actually has your Euclidean parallel postulate. The Klein model actually has the hyperbolic parallel postulate. And I think that I actually showed you that once before. So if you have this particular line that I just drew in yellow, and I have another point over here, because I can have infinitely many chords through this, this chord would be parallel to my yellow line, right? The yellow and the pink lines would be parallel, but this gray line would also be parallel to the yellow line. So we have more than one line that's actually parallel to each line through a given point. Another note about neutral geometry. We study neutral geometry. This is why we're doing it and why we're doing it specifically now. In order to clarify the role of the parallel postulate, in other words, if I don't have a parallel postulate specified, what results still hold? Because some things rely on the parallel postulate to make them work. In fact, that happened on a couple of you guys' exams where you were trying to rely on a parallel postulate in order to prove something else. And we want to know when that's the case and when that's not necessary. All right, another definition for us as we keep moving. We're going to let, and I'll draw a picture of this as I'm working, but let me get a few of the details down to draw the picture from. So let T be a transversal. To lines L and L prime. With T crossing or meeting or incident with, however words you want to use, but T crossing L at B and L prime at B prime. So let me draw what I've identified so far. We have 2 lines. It doesn't say that how the lines are related, so I'm not going to try and draw them parallel because I don't want you to insinuate that they have to be, okay? It didn't specify that. Here's L and here's L prime. And then we have a transversal T that crosses them. So here's T. And T crosses L at B. It crosses L prime at B prime. So this is our image so far. We're going to choose points A and C on L such that A star B star C And obviously we're going to do the same thing with L prime. So, and A prime and C prime on L prime such that A prime star B prime star C prime. One more condition. You probably thought it as I was writing it, but I didn't actually say it. We're going to have with A and A prime on the same side of T. So here's an example. We've got A, B, C. And what I'm trying to prevent as I made that last condition is I'm not trying to put A prime over here. You guys with me on that? They're going in sort of from left to right in the same order. So here's A prime, and then I have B prime and C prime. All right. It's a lot of setup because I still haven't defined anything you didn't already know. All right, so there's our setup. Then the following four angles. Are called interior. And these are the angles. Angle A prime, B prime, B. Angle A, B, B prime. Angle C prime, B prime, B, and I'll mark them in a minute. And angle C, B, B prime. And in our picture, the angles are, and I'll mark them with angle markings like this. There's one of them. Here's 2. Here's 3. And here's 4. So these 4 angles are called interior angles. Another amendment, if you will, or one or more addition to this. Also, angle ABB prime and C prime B prime B are called alternate interior angles. So we have interior, this could have said interior angles. That would have been a little bit more descriptive, interior angles. And then we have our alternate interior angles here at the end. And so are the other two. They aren't not. I'm identifying them. So in other words, which ones did I identify? A, B, B prime. The pink one. Oops. Pink and green. For my picture, the pink and the green are alternate interior angles. The yellow and the brown are as well. Okay. Now, you might be tempted to say, and they're congruent. We have to be careful with that. What condition are you sort of imposing upon my picture if you tell me, and they're congruent? That they're parallel. And that's actually where we're headed next. So this next one is actually called the alternate interior angle theorem. And it has to do with that very fact. This is Theorem 4.1 in your book. And we will abbreviate it for future use as AIA, alternate interior angle, so we don't have to write it out every time. And this is what we know. In any Hilbert plane, If two lines cut by a transversal have a pair of congruent alternate interior angles, with respect to that transversal, then the two lines are what? Yeah, then the two lines are parallel. We're going to prove this, but I want to make one comment before I do, because it's very tempting to take this theorem and turn it around and ask ourselves if it also works. And the reality, here's my note, the converse, and I'll remind you what that looks like in terms of this theorem. The converse of the alternate interior angle theorem is not necessarily true. So what would that mean? What would the converse of this mean? It would mean that if you started with the parallel lines, that you would automatically have congruent alternate interior angles. So going the other direction on this one does not work. And you guys are sitting there thinking, no, wait a minute, I think I remember that it does work. And it does work where? In a Cartesian plane, which is equivalent to Euclidean geometry, or it's a model for Euclidean geometry. So this is a true statement, but that's why it says it's not necessarily true. It depends on a parallel postulate being held. And right now we're working without a parallel postulate being held, okay? So we're going to prove what we actually can, which is the alternate interior angle theorem itself. And we'll go from there. Now, just, actually, let me flip back to the other screen. I want to kind of give the idea behind the proof first, and then we'll do the proof itself. So the idea is to assume the lines are not parallel. So that lines L and L prime have a point in common. And then we're going to actually reflect that point. So we're going to reflect across the line that's transversal, so reflect across T to show they have 2 points in common. That's no good. That's a problem. So we're going to show they have 2 points in common. And that'll be a contradiction because you can't have 2 points in common. Okay, so that's our goal as we're trying to do this particular proof, is to do it that way. So we're going to start with the hypothesis that we have these angles being congruent. So by hypothesis, assume angle A prime B prime B is congruent to angle C B B prime. And this is our RAA hypothesis, right, assuming the contrary. So we're going to assume that L and L prime meet at D. And just for being able to talk about it in a more clear way, we're going to put D on a particular side of our transversal. So we're going to say D is on the same side of T as C and C prime. The proof is similar if it's on, and I'm just going to say the other side. So we're not really being choosy in a way that's inappropriate. It's just making an identification, okay? All right, so we're going to keep moving. By axiom C1, there is a point E on B prime, A prime, that's the ray, B prime, A prime, such that B prime, E is congruent to BD. And I feel like a picture at this point might be helpful, so I'm going to take the picture that we had from over here and try and redraw it, okay? I'm going to make it more obviously not parallel because I want to see that point D just for the sake of being able to talk about all these different letters that I'm mentioning. So here's L and L prime, and here's T. This is L, L prime, T. We have A, B, there's a D. It doesn't actually specify. I don't think I even need to care whether C is before it or after it. It's not so big deal, but there's the C. And then I have A prime, B prime, and here's C prime. And which two angles did I say are congruent? A, B, B prime. So this, actually, we'll just mark them the other way. This angle and this angle are congruent. Everybody good so far? All right, and I had a point E that I just said was existing. So the distance right here from B to D can be mirrored. I can take that same distance and I can flip it around to the other side. So there is a point over here that's E, so that, this looks funny now, but so that, what's wrong? Did I write them in the wrong?
I don't know.
It says A, B. Oh, yeah, I wrote them wrong. Is that what you're saying?
Or like a diagram, or just which one you're choosing. I'm not right.
C.
Unless I'm wrong. Really.
Oh, I did. I marked them wrong. I marked the green ones and I went to mark. I was thinking I had them in the same order I did before, but I put them backwards, so that's fine. You bet. Let me fix it. So this one and this one. Does that fix it, Matt? Thank you. All right, and here's my E that I had before. All right, so let's go this one. This length right here B and B to E is the same as, no, I was wanting E prime, didn't I? How did I say? This is what happens when you transpire in class, is because I've got too many primes going. I should have just used all different letters. That might have been more helpful. All right, B prime, E. So there's a point over here somewhere on this ray. I'll extend my ray to make it look a little bit more believable. All right, here's my point, E. So this length from B prime to E is congruent to the length from B to D. Did I get it all in there now? My picture. B prime D, B prime E. Oh, I marked the other one, didn't I? B E here. Now do I have it right? Yeah. I don't have like this picture in my notes. This is why I'm creating the picture from scratch. This is my problem. Okay, cool. Let's keep going. Segment B, B prime is congruent to itself. That's the reflexive property. So, triangle B prime, B, D is congruent to triangle B, B prime, E by side, angle, side. So let me find my two triangles. See if I listed them right here. B prime, BD yellow. B, B prime, E. Okay. They have the side that they share between them. They have sides E, B prime, and B prime, C prime, the ones on the bottom, and they have a congruent angle. So that's side, angle, side. Those are congruent. Thus, angle D, B prime, B is congruent to angle E, B, B prime. And that's corresponding parts of congruent triangles congruent. D, B prime, B. Those are my other two alternate interior angles. Is that right? No, it's not. D, B prime, B, and E, B, B prime. The other two angles of the triangle, anyway. All right, so our missing angles is that this angle and this angle are congruent. There's a lot of colors going on in my picture at this point. Did I mark them right? I think I did. All right, cool. Since angle DB prime B is the supplement of angle EB prime B, we know that angle EB B prime must be the supplement of angle DBB prime by proposition 314. And axiom C4. Okay, so which two are supplements? Let me see if I can mark them. I need more colors. How about a red? I haven't used red yet. All right, DB prime B, the gray one, is the supplement of E B prime B, the green one. All right, so these two are supplementary, which therefore makes these funny two at the top, which clearly don't look supplementary, right? They add up to 180. Cool. This means that E lies on L. Hence, E lies on L and L prime. And that's a contradiction because that would mean that D and E are both come out of space. On L and L prime. So we have a contradiction. It contradicts property, not property, proposition, excuse me, 2.1. Thus, L is parallel to L prime. Ran into a problem. All right, a couple of corollaries to this particular theorem. So corollary 1. So this is corollary 1 to AIA. Two lines perpendicular to the same line are parallel hence the perpendicular dropped from a point P not on L to L is unique. And this point is called the foot of the perpendicular. That's our first corollary. Our second one says the following. If L is any line and P is not on L, I'm going to shorthand a little bit. There exists at least one line M through P parallel to L. The proof for this uses proposition 316. That's not like John 3:16, just in case you're curious, but it's proposition 3:16. Yep. So what do you notice from all this? What does that mean? What does this last corollary tell us about these different parallel postulates that we have learned about? Both. How many do we start with, Hannah?
Oh, we started.
We started with 3. So there are 2 that are possible. Which one's not? Which one fails corollary 2? No, the elliptic. The elliptic said parallel lines do not exist. And we had a model. It falls apart somewhere along the way with the propositions that we've built up as we've gone. But the elliptic parallel postulate said there are no parallel lines. And this says, well, there are. And the other 2 parallel postulates said that there were as well. That was the Euclidean, where it had exactly 1, and hyperbolic, where there could be more than 1. Okay? So a note on this, a couple more things before we leave. This is our first note. The converse, oh, I already said that. I'm sorry. Look at the wrong one. This corollary, that's the one I wanted. This corollary rules out the elliptic parallel property. In neutral geometry. It worked in incidence geometry. It doesn't work. It's not a possibility for neutral geometry. One more definition and then we'll stop for today. We're definitely related to the last pictures that we've had. An angle supplementary to an angle of a triangle is called an exterior angle of that triangle. The other 2 angles of the triangle are called remote interior angles relative to that exterior angle. So let me just draw a real quick picture of that, so you have an image to go with it. You can pick any angle you'd like to talk about or in reference to this. We'll reference this angle right here. Okay. There are two angles from this diagram that would be supplementary to that particular angle. I'm going to draw one of them in, and then I'll erase it and draw the other one in just so you can see where both of them are. One of them would be right here. Okay, that would be an exterior angle. The other one, if we extended this line, or this side, would be here. Okay, they're both exterior angles. There's two of them. The remote interior angles then would be these two. So this one and this one would be our remote interior angles. And they're in reference to this shaded in red one that I did over here, that exterior angle, or the original one that I drew, either of them, okay? And that's a good spot for us to stop today. We'll talk more about those exterior angles next time.